Good morning, everyone. I really appreciate you all for attending today on a sunny Saturday morning. We will be doing our second BioMedTech Congress with wonderful speakers. I'm an assistant professor in the Department of Biomedical Engineering at Birin University, and I have the pleasure to host this meeting as I have in last year. We have decided this conference virtually this year too. I think this is the effect of pandemic. This made everyone's lives easier. So I would like to thank our biomedical engineering community for preparing this wonderful event and also as our sponsors. So it's my pleasure to introduce our plenary talk speaker, Professor Harila Jiang, an eminent scientist and our former head of department in biomedical engineering, and he's a leader in biomedical research. Harila, thank you for joining us today. We would be honored to hear about your latest research.
Okay, thank you for the nice introduction. As I have pointed out, my talk will be a little bit confused and I will try my best because my data was lost at the last moment. Let me start my lecture. Oh, here are the speakers. Can you see my?
Not at the moment.
Can you see my page?
No, are you sharing your screen?
How do I?
Hocam ekran paylaşımı var aşağıda. Ona bir tıklasanız.
I check that. Video. Share screen.
Ali hocam ekran paylaşımı olmadı mı? Aşağıda ekran
I
paylaşımı.
am checking share screen, but you don't see my screen?
No. Ahmet hocamız basabiliyor mu?
You don't see anything?
Nope.
Share screen. Yeah. Now I think. Do you see now?
Yes, it's starting.
Okay, good. Good. Well, we have some excellent speakers today. We are lucky. You have allocated me a rather long time. So I'm skipping what biomedical engineering is. Sometimes I used to start with definition. But what are the major advances in biomedical engineering? If we list 10, it is the hip joint replacement. This is the first one, because especially the age limits are increasing, and we have many old age patients, and usually they may break their hip joints, and then we have to replace them. And there are some excellent hip joint replacements. Magnetic resonance imaging is also very important development. Heart pacemaker, arthroscopy, heart-lung machine, without which an open heart surgery would not be possible. Angioplasty, bioengineered skin, time-release drug capsules, artificial articulated joints, and kidney dialysis are, as I said, 10 most important developments. I will actually concentrate on what I have done over the years. If you are interested, you can read my notes. Before continuing, actually, I will discuss some important numbers. The age of the Earth is some 4.5 billion years. And the life of Earth, the universe is only 14 times 10 to the 10 years. If we count the number of galaxies in the universe, is about 4 times 10 to the 11. I am giving these numbers because in a moment I will show you that sometimes some things may require impossible, maybe amounts, which may seem impossible to build, but still, once we know the theory behind it, we can encounter difficulties. Now, it was attributed to Bell, invention of telephony. And it was an important, obviously, invention. And soon, just like now, people realized that they couldn't do anything without the telephones. But at the time, the electron, or how electrical currents are flowing, were not known well. So the transmission of the voice was passive. There were no active devices in the loop. So it was not possible to send signals to long distances. For example, communication, telephone communication from, say, New York City to San Francisco was not possible at the time. Some engineers at the time made a computation, and they said we need to develop a device which has an amplification of 10 to the power 129. 10 to the power 129 29, if you compare it with the number of galaxies or even number of stars in the whole universe, it is a number much bigger than those. So people for a while said, this is not possible. We cannot do it. So it is a futile effort to, for example, try to communicate these long distances. But it was J.J. Thomson who showed the properties of the electron and how electron flow produces currents. And it wasn't long after that a vacuum tube was developed by Lead of Forest in 1906. It was called Odeon, but now it is known as a vacuum tube. And using this, he showed that electrical signals can be amplified, and quite soon the problem was solved. I mean, suppose you have amplifiers of 10 magnitude 10, amplification 10. If you have about 129 of them, you solve the problem. So sometimes things may seem impossible, but once you know the principles, things that that were thought to be impossible has solutions. Over the years, I have studied various problems. One area I was interested in was in brain-machine interfaces, developing brain-machine interfaces. This has many uses, especially if there is a patient who cannot use his or her limbs. Such an interface could be very useful. But as you probably know, Elon Musk's new venture, they want to implant everybody with some chip so that they can receive information from the outside world or communicate with machines. So we were using rats for our experimentations, not in human beings. Here you see a rat, and we have actually implanted some sort of chip, but we do use connectors. But there is actually a socket which is flexible. It looks awkward, but it doesn't cause pain. By the way, in the brain, there are no pain sensors, so animals don't feel any pain. So with the help of this chip, we were able to, this was inserted into the motor cortex of the rat, so that we could, by observing signals that we get from here, what the animal wants to do. Later, we wanted to train the mouse to use a robot arm to, for example, feed itself. Initially, this was not easy because actually the rat is a primitive sort of animal, and some other researchers used primates for their work. So we spent more than a year and we didn't have any progress. But later, upon observation, I saw that the problem was with the sort of animal. The animal didn't think that by thinking it could move anything. So it was just using its, I mean, it was moving its head up to the limits and trying to do something. But later we restricted the head, and then magic happened, and the rat learned how to control these robot arms. Another research that I carried out is on was on nerve regeneration. Especially after accidents. If the nerve is severed, damaged, then a person may not be able to use his or her appendices. However, nerves can be regenerated under special conditions, which we studied. First, we designed an equipment so that we can actually stress the nerve, sciatic nerve of the mouse, so that the sciatic nerve is dead, and then one of the say legs is not functional. Then using special optoelectronic stimulation, we showed that it is possible to regenerate those dead nerve cells. And you see that after about 70 days, almost complete regeneration occurred. To test the development, we made the animal pass through this tunnel. Here we put some white paper, but before moving to this part, the animal passes through some stamp, and by looking at the footprints, we have some factor which shows the progress. And Actually, I was planning to have a development period of about a month, but my student who was performing the experiments showed that after 10 days, the animals were quite good. At the time, I was in a meeting in Antalya, but she didn't ask me even. She sacrificed the animals and looked at the under microscope the situation, and as you see from here, the development was quite impressive. This is some of my students. They are performing the experiments. Let me just show you our experiments with rats. The rat presses a lever so that he gets a reward. And he learns to control these levers. I was going to show you. There's something wrong with this recording, I think. Okay, so these rats learned how to control this robotic arm to feed themselves. Another research that I am going to talk about concerns sound. Oh. Here, this is one of my studies concerning epilepsy, how we can model epilepsy, and how we can thought of new ways for stopping epilepsy. That's a long subject. I am going to skip it. Again, if you want, you can read my papers. These are interesting. If you know chaos theory, you may see that there is some order even between chaotic signals. Here is some model, mathematical model that I developed, which can explain what's happening. I try to explain, but I am skipping this part. Models are very important. For example, another model which I did not put here is almost a complete model of the cardiovascular system. This model was built using MATLAB actually, and using that model, we can study, for example, if we cut certain nerves, what happens, which we cannot obviously do on human beings. Another interesting area that I work with is with concerning sounds. Here you see a seaman in a foggy day using some earpieces to locate where a ship is coming. So we built, based on these, a special system. I mean, using only sound signals to investigate what is inside the body. Now, you know ultrasound. Ultrasound signals we apply from the outside, and in order to get good signal back, the amplitude of the signals that we apply are rather large, and they may cause some damage, especially to the cells. In fact, sometimes we burst cells using ultrasound in order to get the inside. So increasing the sound level of these external signals is not a nice method, especially for small children or developing fetus inside the womb. So we developed a passive system based on tiny, really microphones arranged in an array fashion. And the setup, electronic setup, as you see here, with which we could capture phonographic data, and then we can actually convert this into, as you see, these nice three-dimensional color pictures. And we know where we are in the, say this is the EKG of the patient, but where we are. And by examining these pictures, it's possible to see what's happening, whether the heart is normal or that there are abnormalities. This was the picture we got from a 30-day-old fetus in the womb. And this experimentation was done in Bosporus University, very noisy place, actually. It was one of our students. There are some explanations here. If you want, you can read. I'm going to skip. Another interesting study that I did concerns tinnitus. It is the ringing in the ear. Sometimes it could be continuous and quite loud, and the person who has this cannot function. The problem with tinnitus patients is that it is difficult to actually deal with them. And ear doctors do not want to take such patients because they say this is not our problem, and other doctors, they don't know what to do. And at the time, personal computers were relatively new, and I thought, why don't we use a personal computer to test the patient? Because testing the patient takes quite a long time, more than a day, sometimes. So the doctors didn't want to spend that much time with the patient. So we developed equipment so that patient wears some earpieces, and right across the PC. The PC generates some sounds starting from very low levels with certain frequencies. And as soon as the patient starts to hear, he presses a button, and this way a good examination is made. And then we discovered something very significant. We discovered that the tinnitus frequency, the frequency, is the frequency where there is a hearing loss. It matches. So if you give those frequencies that the brain doesn't receive well or very weakly after some amplification, if you give it to the patient, they don't hear these annoying noises, tinnitus noise. If the tinnitus is new, then if the patient uses special signals that we developed, and he listens to this for about a week or so, then the patient is cured. Otherwise, then he or she has to use it every day in order to mask the annoying noise. So we developed some equipment. We have some patents on this also. Okay. Another interesting research was concerning aesthetic sound surgery. I mean, it was the first time anything was done to beautify the sound. Obviously, sound is very important. I mean, some people have really problems and well, their sound quality is very bad, and with dots, that sound they get represented and they get placed in the community. So we did some extensive study what we can do, and we tried to develop spatial surgery techniques to improve the sound quality. And then we developed some surgical techniques, and they were actually very useful. And I have some students who use this technique now. Actually, I have only one, and all the famous singers, speakers, and people who gain money from their use of their voice, actually a patient of this. You can later hear the sounds. This is, for example, a man, but I mean, he wants to live like a woman, but the sound quality gives him, away. So we made a surgery here, and now she's a singer. I mean, you can differentiate that. Okay. Another area which we went into recently is an area known as optogenetics. Now, in the previous study where we inserted spatial chip into the brain, this chip has some micro electrodes at the bottom, and these are in contact with the brain tissue. Although these electrodes are very tiny, still they are comparable to neuron sizes, and sometimes they are inside the neuron, sometimes outside, we don't know. And we get information from about maybe 30 neurons. Or if we want to stimulate a neuron, we stimulate about 30 or more neurons. We cannot address specific neurons. But using optogenetic techniques, we can, if we genetically modify the structure of a neuron, genetic makeup of a neuron, so that it can be excited by light, by laser light. Or if it emits light when stimulated, we can observe individual neurons and also stimulate individual neurons that we choose. So we did some studies with this. I have some couple of doctoral students who just finished, and we know that this technique works very well, but can we use them on humans? Not yet, because we don't know how these genetic mutations will act on human beings. Okay, I think I will stop here. By the way, this is the electrodes. In 1 millimeter square, we have about 64 electrodes. So these are the signals that, and this is the, for example, when a neuron is stimulated, we get this. This is in actual our experiments. Well, as I said, some of my slides, nice slides, are lost, and I think I will stop here. If you have any questions, I have still 3 more minutes, I think.
Hocam, thank you. It was very nice talking.
Okay.
The last research actually that you mentioned in our laboratory right now in genome.
Yes.
In Biruni, we are continuing to, pursue these studies with Sarper Hoca. We're actually using his system, his electromagnetic field system.
We had.
Yes, and thank you so much for this nice talk.
Okay, good.
Thank you, Professor. For our next guest, I would like to invite Professor Dr. Özgür Koray Şahingöz to give his speech on machine learning applications. Over to you, Professor.
Okay, thank you, Melike. And firstly, before starting my presentation, I want to thank you for the Professor Gülçer for his good presentation on his current works and also the technological improvements in biomedical engineering. And also thanks for the committee for organizing this event and inviting me for the second International BioMedTech Congress for a presentation on machine learning topics. Although some of our fields on the study may overlap, I mainly work in a slightly different discipline than biomedical engineering as a computer engineering. Due to some time constraints, I want directly to start my presentation, and my presentation is about the machine learning, and actually I give this topic as a lecture in a computer engineering curriculum, but in this presentation I want to make an introduction of machine learning by giving some relation with the biomedical sciences. And I think my presentation is on the screen. It is shared now. Yes. Can you see it? Yes. Okay.
Yes.
Our topics is on machine learning concept, but before entering this machine learning concept, I want to give definitions about artificial intelligence, because machine learning is a subpart of artificial intelligence. By giving a simple definitions and current situation, its past and its futuristic view. And then I want to use 2 different parts of artificial intelligence. One is about the optimization, and the second part is about the machine learning, which is our main topics in today's lecture. And I want to put some connections with the medicines and biomedical sciences of these topics also. If we look at the historical developments of artificial intelligence, we need to look at firstly what its definitions and what's its content. In the historical development, we can see that there is a content over the movies. And most of you are familiar with these movies and may remember their content. And in this content, we can imagine that this artificial intelligence are directly related with the robotic technologies. Because in this movie technology mainly try to emphasize on the fear on these technological improvements on artificial intelligence and also robotics. And they can present some scary movie on this concept by putting some destructive robots. The first movie can be seen with the Metropolis. Most of the students and also people are not familiar with this, but this is the first initial movie on this sector which puts robotic technologies in this sector in the 1927. In that year, that try to give a futuristic view about this topic, what will be done in the year of 2000. And what will be the technological position of these years? But current technology is much more different from their presentation on that year. But our most familiar topics are fixed on the movie of Terminator and the final movie on the Matrix. And in Matrix, we have a topic about the agents, and we think this agent as an Mossad agent or CIA agent or similar parts, but the agent concept is used as a different notion, as a different research area in an artificial intelligence concept. The main agent means something like this. These are the programs which have some additional abilities on modifying its current environment and also application area. In this concept, if I want to give a definitions about artificial intelligence, it may be think as a science of making machines that can think like a people. The critical topic is in this area, like a people. Thinking like a people may be implemented, but this is a little bit a value point. Therefore, instead of thinking, we try to making some actions on this topic, and we can focus on acting like a people. If we talk about this action, we need to talk about some robotic technologies. It has some hardware issue in it, but in fact, implementation of left-hand side, thinking like a people or acting like a people is not an easy task, and it can be directly said that it is impossible. Instead of this, thinking like or acting like a people, we can talk about thinking rationally or acting rationally concept. Because in this part, in the right-hand side, we have some concrete calculations for making some decisions. In the left-hand side, thinking like people or acting like people, we need to take into consideration of emotional sciences or emotional things. However, in the right-hand side, all our decision-making capabilities are directly related with some calculations. Therefore, in the artificial intelligence topic, we try to focus on the right-hand side, thinking rationally and acting rationally. I try to give this definition at this point because in the ongoing part, I try to give a new definitions for the artificial intelligence concept. Our utmost aim in this four different area can be identified as acting like a people concept. Therefore, this technology is used for the discrimination of the computers with the real human beings by using some programmatic issues. And this may be used as a Turing test simply, and this is a work technology over year by year. And in this part, we try to discriminate of the human being from the intelligent machines over the internet. And this technology can be done in our current internet connection as depicted in the right-hand side. You can check some part as I am not a robot in entering for making some authentication. Or a similar authentication may be done with the use of captcha control. Because as you can see from here, we have some image It contains some text in it, overlooks inquiry, and that can be read only by a human being. Therefore, if there is an entered input over this text field and which fits the correct answers of this image, then we can approve that this is a human being. And this is like a topic that a computer cannot act like a human, therefore we can make a discrimination between them. And in this part, I try to give the definition of rationality. And in rationality, we need to make some calculations. We need to make some programmatic improvements for reaching the maximally achieving our predefined goals, which is given on our problem environment. And in this part, for the increasing our expected utility, we need to make lots and lots of calculations. With our current technological improvements on computer technology, yes, we have this ability. And we try to use this ability for giving the best decisions for our selection. Therefore, instead of usage of artificial intelligence technology, this needs to be renamed as computational rationality. In our current technology, our topic fits on this area, computational rationality, but due to its popular name, unfortunately, the artificial intelligence name is used. And our main aim is, with the use of this computational technology, trying to increase our expected utility. If you look at the details of artificial intelligence, or I can divide this technology into 3 different parts. The first part is about the optimization, second part is about the machine learning, and the third part is about the robotics. If you look at also literature, there are some additional subparts in this domain. But in our current lecture, our current presentation focus on for the first 2 ones. Therefore, I will focus on the optimization shortly, and mainly on the machine learning concept. Optimization, in the optimization concept, we need to talk about, for the maximizing our expected utility, we need to make some optimization algorithms. And the most popular ones about the use of evolutionary algorithms. And they are listed in the right-hand side, like genetic algorithms, anti-colony optimization, simulated annealing, particle swarm optimization, blah, blah, blah. We can use any of them for increasing our expected utility. And for making a simple definitions of the calculation on this evolutionary algorithms, I try to give a simple problematic environment. In this environment, we try to solve a traveling salesman problems in which the salesman needs to visit all the related points on this path by visiting each of them only 1 time. If you try to draw your shortest path, each student or each attendant needs to or can draw different paths on it. But the shortest path is something like this. If you look at this as a human eye, you can decide in a short calculation the shortest path. But in the computational calculations, this has a complexity, and its complexity depends on the number of points on this search area. If we have 10 points here, its complexity means 9 factorial divided by 2. It has about 181,000 different solutions. But from this solution space, we try to find the shortest path. Why I try to show this? Because this is not a huge number. If you can write a simple loop statement, you can calculate each of them 1 by 1 and find the shortest one. However, in our real world domain, we have a very different complex situations. For example, for the United States, our sales points are decided as 532 points. If we try to calculate the new problem domain's complexity, it is something like this. We try to make similar calculations for the factorial. If you try to imagine this value in your mind, any computers cannot make this size calculation. Even if you try to use a supercomputers or a parallel computational concept, this is not possible. It's not possible to find all of these points or check each of them one by one to find the shortest path. Therefore, if you are using an evolutionary approach to solve a problem, you can only say that this may be the best or near to best solution for us. We cannot exactly say this is the best solution. Therefore, for making this type of search, instead of making a brute force by looking at each solution one by one, we need to use some evolutionary approach like genetic algorithms, which has a flow chart as depicted here. The details of this flow chart is not important mainly for us, but I want to show that this is an iterative work. We need to use some looping, some iterations for increasing our maximum efficiency, for increasing our expected utility. And this expected utility depends on our problem environment. I can talk this problem environment in my science on the computer engineering, or I can try to use this problematic environment on biomedical sciences also. For example, if you try to apply this environment on a cancer data set in an iterative approach, you can increase your efficiency or expected utility, as you can see from the following graph. With the use of genetic algorithms, you can decrease the error of your detection of cancer illness, cancer patients. After making 250 iterations, you have a huge detection probability. And similar thing is also valid for different data sets on this area, on this medicine or biomedical sciences. For the iris data set, we can also make similar calculations, and we can decrease our error, mean square error rate, depending on our generation. In this part, I try to emphasize this topic. With the use of this iterative work, I can increase my expected utility with the use of any of these evolutionary algorithms, and this can be applied in any domain in biomedical sciences. If we have some variables, lots of variables, as we did in our variables in this area, these are the number of variables in my problem domain, 532. If you have a huge number of variables, you can assign a new values for it to reach the maximum expected utility. Yes, and there are some literature works as depicted here. I try to find them from the internet for giving explanations related on this optimization concept like this. In the radiology, with the use of imaging technology, we can make a computer-aided detection and diagnosis. And the related links are listed in details in the bottom part. Due to the time constraint, I will not go into details about this, but I can share its links. And also the same topics may be applied on the oncology topic as depicted here for the early detection of cancer illness. And the related work is done by Dropandian and et al. In the ongoing work. And also the similar area is concluded on the cardiology topics, which can be implemented on genetic algorithms for the optimization of our expected utility. And a similar thing is used for the infectious disease detections with the use of artificial neural network, which is one of the most popular machine learning topics, by combining it with the genetic algorithms for increasing our maximal utility to 95% for the detection. And one current work focused on this area is nearly recent work for the clustering of our DNA structure for making a different form of it by optimizing our expected utility. I tried to show the use of optimization techniques in the different medicine or biomedical sciences concept. And the second important part of the artificial intelligence is machine learning. And in the second part and main part of my presentation, I try to focus on this. There are lots of machine learning approaches in the literature. And the upper parts are named as traditional machine learning approach, and the bottom parts are mainly focused on the new and hot topic research areas on the deep learning approach. In this part, I try to firstly mention about some definitions. Some definitions and the ongoing works in the machine learning area. If we look at our current concept, there are lots of application of machine learning in our daily life. All robotic applications or games or web pages or autonomous cars are always needs to use this machine learning technology. In the machine learning technology, we try to transfer our experience of the human beings to the computers. Therefore, this experience, this knowledge should be transferred in a binary form, digital form, and transferred to the computer technology in the machine learning approach. Mainly, we have lots of data. This data can be any type of data, like images, like labeled data, like text, that you can collect from any digital environment. And you can train your whole model with the use of this data for making a traditional classification algorithm, for example, for detection of a cancer disease. And after training your model with the use of previous data, you can test your model on the real data in the hospital, for example. Firstly, for developing your systems, you need to train your model, and then you should deploy this model in a real-world environment. After that, after you've trained the model, you can use your application in many of the following application areas. For example, I can decide a patient whether it's a cancer or not with the use of its current binary values. These values may be images. These values can be discrete or concrete data, and I can use all of them for making a strict classification about whether this patient is a cancer or not. And one of the application area of machine learning here can be focused on the object recognition. What we try to recognize here is about the detection of faces, detection of smile. Why this is important? Because our camera needs to focus on these faces. If you try to focus on the backgrounds, then the faces will be fluid for us. Therefore, the detection of their location is important. Why this detection is important? Because you can make some counting of the related objects in a specific area. Or in our current concept, we can use this image processing, image detections for an application of our works in health sciences. We have some microscopic views as depicted in the bottom part, and with the use of this image, I try to detect whether these cells contains some disease case in our current topic. This topic may be any application area in the biomedical science, for example. Yes, mainly we have a little bit confusing techniques in the right-hand side. There are lots of complicated issues, something like this full connected layers. But mainly, right-hand side is not trivial for us. I try to explain it in our ongoing works. the trivial part or the hardest part is about the collection of our data from the left-hand side. And this data can be collected from hospitals, and our university has a hospital, and we can use this type of data. And these topics may be applied on some sample applications as depicted in the right-hand side. It can be used for web search or computational biology, robotics technology, blah, blah, blah, or with our main topics on biomedicine. Therefore, any application area can be implemented with the use of machine learning concept if you have the related data set as stored in the left-hand side. I try to show its main simple implications on our ongoing points. And after we're making some explanatory work on the machine learning concept, I try to make a simple definitions. What is learning and how we can convert this definition to the machine learning concept. Learning is defined as any process by which a system improves the performance from experience. The main keyword in this definition is about experience. In the human being, yes, we are living organisms and we can store our experience in our brain. However, it is really hard about how we can store our experience on the computers. In our computers, yes, we can store our data. Our text data or numeric data or images or videos can be stored in the computers, but this is not a knowledge. These are only data. For training our model in the computer technology, instead of storing a simple binary values, we need to transfer our brain model to the computer technologies. Therefore, machine learning concept focus on this part, how we can transfer our knowledge to the computers, not data to the computers. Data means images. Data means our selfie pictures with our cellular phones. Data means our videos. Data means this type of text. All of them data. These are not information. These are not learned models. We have to train our computers instead of writing a simple programs on it. And with the use of this machine learning approach, with the transfer of our learning ability, we have the ability of predict the future events. And we are familiar with this issue. If you make some weather forecast over the internet, you may have some predictions about the tomorrow's weather. It can be either rainy or sunny or etc. It can give some probability about the ongoing case. This is not a strict definition. There are some probabilities for this type of predictions. Or similar thing is also valid for the detection of some illness. You have some probability. For example, about the detection of COVID-19, we have a probability of detections. Yet it's maybe a high probability, but we cannot say that this is always true. And you have lots of this type of experience in your previous life. And also with the use of this technology, we can transfer this learning in an interdisciplinary way for the application on different discipline or implementation areas. Therefore, these application areas can be experienced on health sciences or computer technologies or even pharmacies or etc. If you set up your systems in a concrete manner, you can apply them in any type of discipline in your area. In this part, the critical definition is that in the computer technology, we talk about the left-hand side. We make our programs, we write our programs, and during these programs, yes, we have a data, and our programs process this data and reach some result. But in the machine learning concept is a little bit different from this. In the machine learning concept, yes, we have a data. We have a huge image sets about the cancer detection. And also we have a results. These images are labeled, whether it's cancer or not. We have a data and we have a result. And our computer technology learn by the use of these data and results, and implement its own program. This is what I try to explain as learning. This is in fact not a real program. This is a learning. This program definition and the program definition in the left-hand side, they are not same. In the left-hand side, we have some strict rules, some conditional statements like if then else, or we have some loop statements, we have some sub-programs, or etc. However, in the right-hand side, we have some deducted systems. And these systems program is implemented by our computers. And this is different definitions of program from our traditional knowledge. Therefore, it is named, if we generate these programs, this is named as a machine learning. Because this program is written, this deduction mechanism is written by your computer, by your system. And this program writing learning experience can be applied in any of the following applications area. And in this part, I try to use some detection of anomalies. Sorry, I missed my mouse. Detection of anomalies. This can be in the detection of a network transfer, or these anomalies can be in our health also. Also, we can use this technology for face recognitions, or we can use this for medical diagnosis, or etc. This application environment has a huge application area for us. You can use this technology in any of the real world application, and currently most of the applications use this. And you have experienced this issue in your daily life also. And with the use of this machine learning, we have two different definitions. The first definition is about the regressions, and second definition is about the classifications. I try to give these definitions because my ongoing work focus on this. In the regressional analysis, I try to decide a strict value on our application environment. For example, I try to predict the price of a house. And imagine in our current economical conditions that our house prices are increasing day by day. And you try to make an imagination about what will be the price of my house after 1 month. This is a prediction. This is not a concrete value. Therefore, in this part, we try to reach a continuous value in this area. But in the classification, we try to make a discrete classification for us. For example, if my data is a Twitter text, I try to classify it whether it contains a positive response or negative response. I have two different responses. If I have an image of something like this in the right-hand side, I try to classify them either it is an anemic cell or a healthy cell. There are some discrete positions in it. Therefore, with the use of machine learning, I may have two different applications area as a regression predictions or as a classification predictions. And many of the application areas of the biomedical engineering or health sciences focus on in the second part. Classifications in the classification concept. For example, in the health sciences, heart disease detection systems for the cardiovascular technology can be focused on this. We have our data set as depicted in this slide. in the slide, we have some features of our patients as depicted in the bottom part. These are the features of each patient. These are the input data. And with the use of this input data, I try to detect whether this has our target variable as whether it has a heart disease or not. This is not a doctor system. This is only a decision support system for doctor. You can make an analysis and you can give some output for the doctors for reaching a real detection system. Therefore, by implementing of our original values in the left-hand side, we try to reach either we have a heart disease as a true value or not. And our patients has the following values. And if you want to get these values from hospital, you can easily get this with use of ethical committees. And the feature types and numbers are important for us. As you can see from here, we have many of the features. In fact, we may have about 10,000 features for a specific, for a detection system. But it cannot fit in this slide, therefore I put in a limited version of it. But for example, my last study contains about 8,000 features in it. But in this part, we have a feature about 7 features. And as you can see from here, they are numeric, some ones. These are character features. This is a Boolean features, and this is a textual features. However, in our machine learning approach, we can only accept a numerical features. Therefore, we should prefer the use of some data processing techniques to transfer of these data to the numbers. For example, instead of male, I can say that this male should be 0. Instead of female, I can say that this value should be 1. There are some engineering approach to this, but this is not our main content. I try to emphasize this, our input should be numeric for training our model. And after the training our model, what's our main aim is this. The previous data set is gathered from the hospital from our previous experiences. I store this data. These are data. These are not a learning. By using this data, we train our model and we implement our program by our computer systems. And this is a learning. And with the use of this trained model, this learning systems, I try to define whether my new patient is contain a heart disease or not. This is our main detection system, because this detection will be done on the futuristic view, on the ongoing patient detection systems. And depending on this, it says that, yes, you may have a heart disease. This is not an exact detection. This is only a decision support systems. And this is given to the doctor for making the real detection. But if you make your previous experiences, you can say that this has an accuracy rate about 95%, for example, because your previous experiences give this type of accuracy levels. And this model is used in the first type of classifications, and this is named as a supervised learning model. In the supervised learning model, we have labels in our data set. But if you look at our current technological improvement, we have a huge data in the internet, and most of them are not labeled. Therefore, if you try to deduct some important information from this huge unclassified data, you need to use an unsupervised learning technology. In unsupervised learning technology, yes, we have a similar structure of data like this. We have a data, And we try to classify these data to different groups like this. This is our first group, second group, or third groups. And these classifications can be done on the same data set as depicted here. Yes, we have some heart diseases, but we may have different types of heart diseases here. It can be either on the patient type 1 or patient type 2 or patient type 3. They depends on different cardiovascular systems of the human being. Because heart disease have these different types in it. I am not expert in this area, but perhaps it may contain 100 different types. Therefore, these types can be grouped without labeling value. I have only a labeled value like whether it has a heart disease or not. There is no type in here. It cannot define this is a specific type. It says that there is some specific grouping here, but your expert, your doctor needs to give a definitions for what type, what should be the name of this type. And for the deduction mechanism, this is very important because in this part, we have a huge unclassified data. With this unclassified data, we try to deduct a new illness, for example. Therefore, this may result some great invention. However, in this part, it is more usable in the real world because it is the transferring of our current technology as an expert systems for the usage, but this is a deduction mechanism. After the training, yes, we can define, I have a type 2 illness here, but there is no exact name of it. This exact name should be given by the doctor. And I try to show its flow chart as depicted here, but the details is not important for us. The critical part is this is also an iterative approach for us. In optimization technology, we also have an iterative approach. In the machine learning technology, we also have an iterative approach. And iteration means computational power. Therefore, our computer should have some capabilities, some programmatic abilities or application abilities, and we need to use these technology. And our machine learning workflow is for this. In the main manner, we have a raw data. By processing this raw data also contains labels. We try to reach our learning mechanisms in the right-hand side. Our learning knowledge is this. And this knowledge, this right-hand side, contains some programs in it. But this is not a simple programs like Python or like Java or like C++ or etc. In these models, we need to use some different machine learning algorithms. Our traditional machine learning algorithms are named in this part. I miss my mouse. Named in this part. And with the use of this traditional machine learning approach, we can make some simple implementations for regressional analysis like this, or for the classification analysis like this. But with the traditional machine learning approach, the discrimination of data as depicted in this type data set is not important, is not possible. Because this is not regular. For example, our X value is 5, and we cannot directly say that whether this is in the class of plus or square. This is not an easy way. Therefore, instead of usage of traditional machine learning approach, we need to prefer neural networks approach. This neural network approach mainly applied on a non-linear data sets, and it gets the use of our human being evolutions and brain execution as did in neurons. And the neurons, we have lots of synapses, and we can collect our data and transfer the collected data to the ongoing part here. And it is transferred in the same manner. We can collect our data with the use of dendrites, and we can transfer our data by forwarding it into the right-hand side. And with the use of this neuron, we can set up our brain systems as depicted in the left-hand side. And these learning mechanisms can be transferred in the computer technology in the right-hand side. This is our real world. This is our computer technology. Therefore, if the similar structure can be set up on the computer systems, I may, not a real value, I may transfer the learning of the human being to the computer technology. Therefore, my aim is trying to set up this type of data structure on our computers. And this data structure is something like this. These are all of them are neurons, and we can connect them one by one with each other layers. Therefore, this structure is named as artificial neural network. Yes, I can set up this artificial neural network, but what is learning? What is program here? I try to show this simply. What is program? What is our learning mechanism? And in the training of artificial neural network, its flow chart is similar. And please be careful about the similarity of this work with our previous definitions. This also have iteration. And this iteration means calculation. This iteration means processing power. And with the use of this iterative work, I can use an application area like this. I try to detect whether this value is 0 or 9. As a human being, I can easily discriminate it. This is something like acting as a people. But our computer technology can also define these values. This is 0. But if you get some more complex values like this, whether this is 8 or other, it may be somewhat trivial for us. Therefore, we need to use some training models. Our models is trained with lots of data like this, which is named as MNIST dataset for the detection of handwritten numeric values. And our model, artificial neural network model, is set up depending on our data as depicted in the left-hand side. This is my image. And my image contains 28 times 28 pixels in it. 28 pixels in the column, in the row. And if you multiply them, we have totally 784 pixels. And each pixel is the input of my artificial network. And this value can be either 0 or 1. If it is black, you can define this as 0. If it is white, you can define this as 1. These are our input values. And after the training model, I have 10 different outputs. If this value is 0, then this value is sent as 1. This is for 1, this is for 2, this is for 3, blah, blah, blah, and this is for 8. This value is 8. Therefore, in the flow chart of this diagram, this value should be transferred as 1. What about the others? All other values, all other neurons transfer their value as 0. Therefore, this is a classification mechanism. Our data is this. Sorry, our data is this, and I classify this image as 8. This is a classification of a simple example like 8. And similar thing is also valid for the classification of a cancer data, or similar for a iris data or heart disease data. I have similar input parameters, and all of them must be numeric. And defining on them, I try to classify my data in the right-hand side. And what is our learning? This is critical. Our learning is this. As you can see from here, in my lecture, I try to show it's engineering details, but this is not important for us. Our neural network contains this type of structure. These are neurons. Neurons are not important. The only important thing is about these numeric values. These numeric values are the weight of these links. There are lots of links here. There are more than 1,000 links here. And it means that I have more than 1,000 number values, weight values of each link. Therefore, learning means, or trained network means, this weight matrix. All these weights, number of these weights is named as our learning. This is not a program. I only store these values in my computer. And this is something like in our brain. We only store some weights, some values in our brain. And same thing is valid for the computer technology. We only store these values, these double values or floating point values in our computer as a learned systems. Therefore, if I trained my model in a computer, I can only transfer these values, numeric values, from one computer to another and transfer whole my experience to other part. This is not possible for human being. If I have some experiences, I cannot transfer my knowledge, my brain data to anyone else. With our current technology, as I know, it's impossible. But in computer technology, yes, this is possible. With these values, I can train a great decision support systems for doctors, for example, and I can send this for any countries, any continents in the world. Therefore, this has a great improvement in this technology. And the calculation of these values is a little bit trivial for us. And this is valuable for the computer engineering, but I try to show their calculations like this. There are lots of derivatives or integral types calculations, and you need to calculate all of them with the use of different and complex values. And if you look at these calculations, it's a little bit scary for us. This is frightening the users, this is frightening the students. But in fact, our current technology makes it very easy for us. There is no need to know all these calculations. There is no need to know the mathematical background of them. We have some libraries like Python or TensorFlow, Keras, Scikit-learn, or etc. And with the use of these technologies, any students or any novice person can easily implement his system. For example, the implementation of a trained model in Python, Scikit-learn, is something like this. It contains about 10 lines of code. All the related implementation are done by the related library. There is no need to know the detailed engineering knowledge about it. By only the usage of this technology, we can implement some complex, some trained models. Therefore, with having some basic knowledge, we can implement our machine learning model or even deep learning model in our ongoing work. I try to show this. Machine learning is not a trivial issue. After these points, with the use of related libraries, we can easily construct them. There is no need to make some looping statement in it. For example, in this part, it says that we have 3 different layers. All of them contains 13 neurons in it. And I try to execute my training model 5,000 times. And it says that I have, I have first layer as 13 neurons, second layer as 13 neurons, third layer as 13 neurons. I easily construct my network on the artificial neural network concept. And I execute this, train this model with the 5,000 iteration. But its main concept is executed on a single line of code. And this is, we have this ability because we have the usage of the related libraries. We are using the scikit-learn libraries for training the whole model for multi-layer perceptron classifier. This means artificial neural networks. Therefore, if you are not familiar with this concept, you can easily start this technology to implement this on your application area. And this topic is valid for the machine learning concept. The second part or enhanced part of this focus on the deep learning. And deep learning is a relatively new concept for us. And currently, this is a hot topic research area. Because in the deep learning concept, we need to use a big data in it. In our traditional works, in our previous machine learning concept, we are using our model with a traditional Excel-based data sets. But in this part, we can use a huge big data concept. In this big data concept, what is big? The big one is about data. What is deep? Deep one is about the increase of our layers in the artificial neural network concept. What does this mean in this concept? Yes, in the traditional way, we have a neuron structure like this. We try to modify this structure by adding some additional calculations in them. I will not go into details about this because this also can be executed on our libraries. And their structure is something like this. This can be in an engineering view, but details is not important for us. But important for us is this. This is a traditional artificial neural network. This is a deep neural network. Why it is deep? Because we increase the number of layers here. We increase the number of connections here. And these increments also increase the accuracy of our detection systems. And in this detection systems, one important topic is also critical for us, for the image. And each image, this is an image, and this is a colorful image. And a colorful image can be designed as RGB format. RGB means red, green, and blue. This is the red text, this is the green text, and this is the blue text. And we can process this instead of a single image as depicted is in our MNIST data set. This can be transferred to the 3 different dimensions as red, green, and blue. And these images can be used in a convolutional neural network approach for a deep learning models. Please be careful about the number of layers here. What is deep? Deep one is about number of layers. And the convolutional neural network has a great effect in the detection from the images. And this concept is related with the biomedical science concept because we need to work most of times on this image data. And I try to show the deepest part of this technology. Yes, we try to increase the number of layers. And this is on the AlphaGo systems. This is the number of layers for the GoogleNet inception model. Please be careful about the number of layers. Each one is a different layer. This is another different layers for us. Please try to imagine the size on the in it. Yeah, I try to show the increment of this number of layers because if you increase these layers, you increase the processing needs. Therefore, if you are using a deep learning approach, you are using a big data, and therefore you need a big processing power. With our current technology, yes, we can use a supercomputer, something like this, which is used for the AlphaGo system. And in the systems, you can use more than 1,000 CPUs, central processing units. and you can contain 200 different GPUs on it for increasing the processing power. Our current technology on this, our current computers contains not this type of a supercomputer technology, but we may contain some GPU technologies on it, especially for game computers. And, they have some graphic cards, and they may have more than 3,000 cores in it. And with the use of this technology, you can make some parallel processing, and you can increase your processing power for the detection, execution of the machine learning or deep learning model. And this is the end of my slide. I try to urge in the final points. I try to finish and obey the time constraint. Therefore, thank you for listening to my presentation. And if you have any questions about these points, I can directly answer it to you.
Thank you, Professor. Dear participants, if you have any questions, we can take those right now.
Özgür Hocam, thank you. It was very, very great to hear from you. I have actually two questions. As a cancer biologist, first of all, it's very exciting to see that cancer can be predicted. So my first question will be from the first one. Based on your ant tracking experiments, which I will relate to that, to cancer related projects that I am on in. So is it possible to confirm your data, your prediction data, where the ants will orient this way or that way? How do you confirm that?
Yes, mainly we have a data set as depicted here. I try to show it. Oops. Yes, this is the code. Mainly we have a data set about 10,000 data, for example, or this can be about 10 million data. And you divide this about two parts as 8,000 for training and 2,000 for testing. And all of them are labeled, and you know whether this is a cancer or not. And with the training of model, yes, you set up your model, and all of this setup directly related with this 8,000 data. Therefore, testing the accuracy level with this is not a good approach. But this is an untouched or untrained models. You can measure whether you generate good detection systems or not by using these data, because you have classified them. Therefore, yes, you can measure your accuracy level with this type of data. This is possible.
Okay, thanks. For the second part, you mentioned that learning detection can be based on gathering all the features, and you said you can put up to like 900 features in a data set. My question is it does it become too complicated when you have too many features to make the prediction data?
Mainly, we may produce about, in my latest project, I have as 8,115 features in it. And if you use all of these data, you may reach a detection rate about, for example, 75%. But if you decrease this value by making an appropriate feature selection mechanisms, you can decrease this about 100 features, but you don't know which one is the best features, and you may reach about 85% accuracy. And this is also an academic or research work for us, which features can be detected. And these features can be detected with the use of optimization algorithms like evolutionary algorithms. This is also in the same topic. They are all related with the artificial intelligence. But the critical part is about data. If we have a huge data set, we can choose the best of them. We don't know which one is the best. As a doctor or as an expert, we may some expectations about these features may be important for us, but in the real world, in the real implementation, it may have no effect on the final detection.
Thank you. Thank you.
Okay, I thank you all also for the other attendance.
Are there any other questions? Okay. Then thank you so much, Professor,
Okay,
for your
thank you.
presentation. It was really nice and really effective. Our next guest is Dr. Abdurrahman Kamuran Kadıpaşaoğlu. His speech will be on design and numeric evaluation of a novel axial flow left ventricular assist device. Over to you, Professor.
All right, thank you. I really appreciate the invitation
Yes.
to give this talk about our research at Yıldız Technical University. So let me start sharing my screen. All right, can you see the screen now?
Yes, it's clear.
Yes, we can see.
Excellent. All right, and I'm trying to make this disappear. All right, now we're ready. Okay, this is going to be a talk about our research funded by TÜBİTAK. And the topic of the research is the design and testing of a mechanical circular support system, which we've been conducting at Yıldız Technical University for about 4 years now. And this July is going to be the end of it, but we're probably going to apply for an extension because of the delays due to the pandemic and etc. And hopefully we're going to get it done. We will be continuing this research for a while, I guess. So the topic is the treatment of the underlying disease, which congestive heart failure. In the great drawings of Dr. Netter, you can see that it affects mostly elderly people, but it doesn't actually depend on the age. It can attack any time, at any age, but mainly the elderly population, which is increasing now, as you know, as the expected age, average age is going up. And it could happen acutely, or it could happen in the chronic phase. So, and it's a long disease. It takes a long time to develop. Actually, there's like years in development, and usually at this stage, when it reaches this stage here, the patient is totally incapacitated and cannot brush his teeth, for example, or climb a couple of flight of stairs by himself. So usually at that time, he is also non-responsive to medication, and the only possible way of treatment would be a heart transplantation. But unfortunately, the donor numbers being a mismatch for the patients on the waiting list, a transplantation is not a good 100% effective treatment for this patient population. So since 1960s in the United States, in Japan, and also in Germany, people have been conducting research on these VADs, which is ventricular assist devices, or as the title of my talk says, mechanical circulatory assist devices. It could have the left side of the heart, the right side of the heart, or both. In that case, we call that total artificial heart. The machines have come a long way as well over the years as technology developed. The first generation was really big devices which were prone to malfunctions, as they had valves in them and flexible membranes and such. And they had huge controllers which anchored the patient to the hospital, so you couldn't discharge the patient, and the patient had to push his console as he or she walked around the hospital. But these devices really proved very effective in increasing the survival of these patients. This was a study that was published in 1992, which was a landmark in that research, the Rematch Trial. And as you can see with the assist device, as opposed to medical therapy, there's a clearly advantageous survival curve. Now, not only as a bridge to transplant, but these some of the patients are contraindicated for transplantation. So like if they cannot take immunosuppressants, like cancer patients, for example, and such. So in those patients, we put the pumps in as a permanent device until their demise. So that's called destination therapy. In some other cohort of patients, for example, young perinatal mothers who have acute cardiac failure, or viral patients in which the heart failure is reversible. As soon as you cure the virus, the heart recovers. Then you could provide assistance to these hearts for a limited duration until the recovery, and then you can explant the valve. So they are really a nice tool for helping this kind of desperate cohort of patients. As the technology evolved, the second generation ventricular assist devices started to appear in the late 90s, and these were very small, like finger size, implantable, and totally portable devices. So you didn't have to be attached to a console, and you would leave the hospital, be discharged, and then live a perfectly normal life on these pumps. And the first experience with this pump, this type of second generation pump, was in 2003 in Turkey with Deniz Cihan Küçükaksu, who also started his own endeavor to create a Turkish pump, as we call yerli ve milli pump. But it's still coming, you know, it's still in the coming. They decided to work on a centrifugal pump, and he's still working with Koç University, İsmail Lazol over there, and their pump is still in the works. They are still doing animal experiments. So about that time in 2007, we came back to the country, and we started our own research on a alternative technology, which would be called axial flow as opposed to the centrifugal pump. At Yıldız, we gathered a nice team of experts with Dr. Akay, who was a Baylor cardiac surgeon, a well-known expert in transplantations, as our consultant, medical consultant. We applied to TÜBİTAK and got this 2003 grant, which helped us establish a laboratory. So what we decided to do is a second generation pump, actually, which consists of three primary technologies. The pump itself, which is consisting of a turbine, as you can see here, that takes the blood in, and the rotor gives kinetic energy to the blood, and the diffuser transfers this kinetic energy to potential energy, to pressure energy. So what the pump does is increases the flow, maintains the flow, and increases the pressure. In that way, taking blood from the left ventricle, which the heart cannot pump because it's failing, and in parallel pumps it to the aorta. In that way, it's a ventricular assist device. And of course, it needs a motor, which is composed of a DC motor, brushless DC motor. So you need to make those. And then the control unit is very important. This is where the pump DC motor is attached to a controller, which adjusts the RPM, the speed of the rotor, so that it adjusts the amount of blood that is sent to the circulation. So if the patient is exercising, for example, you increase the RPM, or if the patient is sleeping, you just decrease it. And the batteries and all that, the cables, the connectors, the graphs, the batteries, they make the third primary technology, which we call accessories. In our grant, we decided to do the primary technology and the secondary technology, and we left the design of the controllers and everything until after the technology readiness level 6, after the design freeze. And of course, another job that we set ourselves for doing was the performance testing platforms. Of course, you cannot design the device and just give it to the doctor and say, here, just go ahead and implant it. You have to test its performance and demonstrate it. So the demonstration phase in the full scale is important, and in that towards that goal, you have to make a mock circuit of the circulation so that you have a setup, a rig that operates just like the cardiovascular system, creates the same hemodynamics, and then you put that mock circuit into failure and you attach your pump to it and see if it helps. This is very important because it reduces the expenditure in the next phase, which would be animal experiments. Of course, your reduction of the number of animals that you sacrifice is an important task, and there is cost and time involved. So this is an important part of our project, not just to make the technology, but also to make the technology to test it. And the first part of the design is in the SolidWorks in computer. So you design all three parts of the thing: the inducer, which aligns the flow into the blades of the rotor, and then the rotor takes it, as I said, spins and adds kinetic energy to it, and then the diffuser kind of like puts the brakes on it and transfers the kinetic energy into potential energy. So we first design the pump elements in the virtual environment in SolidWorks, and then we pass on to this program called ANSYS, which performs a test we call computational fluid dynamics. It tells us in the virtual setting how blood velocity profiles are happening through the pump even before you construct the pump, produce the pump. You can test its performance in the virtual environment. Like, for example, here there are a lot of separations from the blades, and there are a lot of turbulence at the exit, and there is backflow and stagnation points. So the things that you have to be careful about are you shouldn't let blood be exposed to too much stress. That's one, because then you destroy the red blood cells, and which are the elements that carry oxygen to the blood. So kaş yaparken göz çıkarmak gibi. And then you have to prevent blood from stagnating, which is like coming to a very low speed, because then it coagulates. Then the pump sends these clots into the body, and then you cause paralysis and embolism in the end organs. So you have to adjust the geometry so that you get a very nice flow outside of the blades, outside of the diffuser, as you can see. So this is called the geometric optimization, and you do this by iteration. You see these eddies and everything, then you go back to SolidWorks, you change the angle, and then you come back, and then so it's an iterative design process. And through this, we also look at the I'm sorry, this is in Turkish, but we look at the efficiency, and at the point where the efficiency is maximum, there's then a drop off. This is the point of diminishing return. So we stop there, and then we set the geometric elements at this point. So we freeze the design, so to speak, at this point. And then this tells us also, the ANSYS program, exactly where these blood molecules are going. Actually, very, very useful technique. And you can see that here some of them are going back. You can see here some of them are late, which means that it's stagnating, and some of them are going actually back inside. which is something that we need to wash the turning, roller bearings of the pump. So this is designed intentionally like that. So we improve the design like this until we get our hemodynamics and mechanical properties. As you can see, an efficiency of 21.5 is pretty good for a size, this size engine, with a low energy demand, low power demand, as you can see. And then the pressure rise is about 80 millimeters mercury, acceptable. And a flow of approximately, if this is 60 milliliters for a heartbeat of, or 70, for a heartbeat of 60, you get about 5 liters per minute, which is what the normal circulation requires. So you try to optimize the design for hemolytic properties, first of all, not to destroy the blood or cause embolisms, and also for hemodynamic parameters. So it's a combined task. And after that, the optimization, you produce the pump first in plastic. This is polylactic acid version of the pump, or prototype, which we did in our 3D printers. And then you optimize the size and all that. So once you do that, the next phase begins, which is the physical testing platform. And for that, you need a, if you're going to put the pump here in your circuit on the bench top, then you need a low pressure reservoir, which the pump is going to take the blood from, which is like the heart. And then you need a high pressure reservoir, an afterload reservoir, in which the pump is going to send the blood against that pressure. That is the afterload. So preload and afterload reservoirs. Now, as much as the pump pumps here, you have to make sure that the same amount returns back, so that neither these reservoirs overflood or they run empty. So you have to have exact amount of return and outway blood. So you have to adjust this resistance in your on the bench test setup. And we do that by using a gear pump. So we adjust the spin rate of this pump, exactly matching the outflow of our test pump. So this is something that we get from outside, and that of course is one of the causes that delayed our protocol because of the supply chain problems with the pandemic. Here's the gear pump, as you can see here, and these are the two reservoirs in the laboratory. This is a conventional pump that was placed there just to design this setup before we had our own pump ready. And you have to, of course, create the pressures, and you cannot create them with just water. So what we do is we pump air here. We have pneumatic actuation in order to create this thing. And of course, let me go back 1 second. Now, in order to place our pump in the circuit, remember that the pump doesn't have a motor at this point, so we have to spin it externally. So we have to design an external drive mechanism here with a driver rod and an inlet and an outlet. We put the pump in here, the torque sensor, some couplings and everything, and a DC motor. So this is what we design in the Simulink as well. We get a really nice motor there to drive it that we can control as we want. And then we design the acrylic block in SolidWorks, and then we make sure that all the dimensions are correct and everything. And the production of it is really takes expertise, and we do it at Kocaeli University with our colleague over there, Dr. Sarkan. He's a really expert in machine machining and production. So he does this machine for us, the whole thing, the whole setup, which we finally insert in our test external drive mechanism. We can see the gear pump here. We have flow probes for the whole circuit. This is a laser that I'm not even going to talk about in this lecture. It's another setup. So we have the controller of the bed here. We have the D-space for data acquisition, and these are the valves, pneumatic valves that we open and close in order to create the pressures in here, and the flow sensors and the gear pump. So the whole thing is ready. Of course, it takes a lot of electronics, a lot of control, a lot of power supply. So our students have designed this box all by themselves in order to collect all these wirings. Otherwise, it's like spaghetti, the whole laboratory. You cannot really manage it. And of course, this mock circuit cannot consist of just 2 reservoirs. You're talking about the whole cardiovascular system with end organs and the capillaries and the return system and the right ventricle and the lungs and everything. So you really cannot do that with just 2 reservoirs, an inlet and an outlet reservoir. You have to have, in order to create the inlet and outlet pressures of the ventricle accurately, of the pump accurately, you have to have a design. But to make this, to create this on the bench top is impossible almost, because you need many reservoirs that you need to control. So a very convenient solution to this is to construct a hybrid circuit. The complicated part of the circuit is in the computer. All right, it has the left ventricle in it, the aorta in it, the pump intervening there in parallel, and then the venous circulation, the right ventricle, the pulmonary circulation, the left atrium, and all that, the valves and everything, and the capacitances and all that, the resistances. All that is simulated in the computer, and all that the physical circuit sees is the aortic pressure and the ventricular pressure. That's all. And then you move through the interface to the physical system, to the ventricular assist device, and then all that you have to do is to produce this these pressures at these interface points, and then return, and then the flow that is created by the pump is returned back to the numerical system as numeric data. So this is a really nice way of creating a very accurate model in a very simple physical setting. And then you can create, as you can see, these outputs that pretty much simulate the left ventricular pressure, the aortic pressure, the left ventricular volume, left atrial, pressures here in a very accurate way. And also we can reproduce here heart failure. These are the pressure volume loops. This is for a healthy heart, for example. The pressure is 120, as you can see, and the volume is about from 45 milliliters to 120, so 80 milliliters per beat. And if you're working at like 70 beats per minute, that means 5.5 liters per minute, which is a healthy heart. And then you put this heart into failure, and you can see the red here. So the volume that's every stroke ejects into the body is reduced. The heart cannot unload the volume that's being sent to it by the venous return. So the heart is overloaded. And when you put the VAD in there, the pump, the VAD at different increasing speeds is going to unload the heart, volumetric unloading. So you can very nicely simulate the whole situation in the numeric part of the circuit. And then you have to, of course, control the pneumatic valves. So you calculate the control law here, and then you implement the control inside the pump, inside the whole circuit, and then you test it. For example, this is the this is a very normal reference. For example, a very simple sinusoidal curve. You want the pressures to be sinusoidal, for example, in these reservoirs. All right, a very simple example. But then you get these very noisy results, and then you have to eliminate the sensor noise. So you use Kalman filtering. And then we implement all these in our pumps. And certainly in the dynamic equations, there are these constants that the pump has. Right? These are the parameters of the pump, so you have to define those. And then that's another thing that we do. We estimate the parameters. We do inlet-outlet estimation schemes. We use the system identification toolbox in MATLAB. And by giving which angular velocity, which we can adjust, and which delta pressure, the difference of the pressure between the two reservoirs, into the pump, we estimate the output of the pump in terms of flow, milliliters per minute, and the torque that it generates. So input-output estimation, it's a transfer function estimation scheme that we use in order to estimate it. And then we can pretty much guess the transfer function of these. And then finally, we give the reference as we give the left ventricular pressure as the reference, the aortic pressure into the second reservoir as the reference, and the flows as the reference in a normal heart. And you can see that the pressures in the reservoir follow the reference quite satisfactorily. So you have a good control system for the pneumohydraulic interface. And this is when the heart is normally working. This is when the system is failing. And this is when the system is failing, but it's being assisted by the pump. So this is so far so good. And then you need to control the pump itself with the patient controller. So we write a backstepping Lyapunov-based controller for this. And then we decide on the reference signal generation for the ascending air, how much the patient needs for every single moment of his or her physiology. All right, what is the metabolic need of the patient? So we estimate that, and the pump automatically adjusts itself, its own revolution per minute, according to that demand, according to those disturbances in the environment. So it's not only reference tracking, but also disturbance rejecting. And also we are determining the reference itself with the scheme. It's a backstepping Lyapunov-based controller, which actually works pretty good. As you can see here, this is the reference in red, and the blue is the actual flow obtained by the pump. So it's almost with no error following the reference. And you can see here that this is the aortic flow, and this is the left ventricular flow of the failing heart. And if the aorta tracing doesn't touch the ventricle, it means that the ventricle is not ejecting, which means that the aortic valve is staying closed, which is not something that we want in our patients, because then the valve is going to calcify and it's going to have clots underneath, which are going to be ejected into the coronary circulation, causing even more damage to the myocardium and also to the end organs like the brain or the kidneys and everything, causing emboli and infarcts over there. So we want the aortic valve to open at least intermittently to wash out the deposits that accumulate over there. So the one of the constraints of the control scheme with the Lyapunov-based controller of the pump, for the pump to automatically adjust itself, which is something really not in use today in the clinical arena. These pumps are being used everywhere, like about 5,000 a year around the world, but all those pumps are being adjusted manually. So the patient has to turn the knob to reduce or increase the velocity of the pump. So this is going to be something new, actually, hopefully, if we can implement it in the clinical setting, a self-adjusting left ventricular assist device. lastly but not least, of course, the motor. This is being done at the Aegean University under the auspices of Dr. Erkan Meşe, who was recruited from Yıldız Technical University over there. So what they are doing is they are designing it in the numerical environment first, and then they are producing it meticulously by hand. As you can see, this stator, and they are these stator windings are have to be done by hand on a micro scale, very meticulous job, and they are producing these motors and they are testing it with, if you remember the slide that I showed, 8 watts, 3.8 watts. This is how much the motor has to generate for us. And then it also has to adjust the acceleration, because the controller scheme requires that the blood flow increase and decrease at intervals in synchrony with the heart. So, and then this is the next step actually that we're gonna be doing afterwards. We are done with the motor, we're done with the turbine, so we're done with the platforms, the testing platforms. So what we're gonna do is we're going to integrate the sub-technologies, the motor and the pump, the motor and the turbine to create the pump, and then we're going to put the pump into our Mach circuit. So it's going to be the next phase in our studies. And before I close, I finish, I really want to stress a point, important point here. All our students, all my students in the laboratory are undergrad students. I had 2 PhD and 2 master students that are gone now. So all we have is undergrad students, second year, third year, senior, sophomore, senior, and junior year students. And they really, from the first year on, they enter the lab and they learn, and they even, publish. They start publishing at this young age. We are now at the critical point where we can fire out 5 or 6 publications, and that really excites them. The Mach circuit team, the external drive mechanism, and the graduate students, and also we have the rookies that we take in from the first year or second year, and then they undergo a training program in the laboratory. We teach them how to make tea, how to clean the floors and everything. And then when they are ready to serve in the laboratory, take them, and then we start using them. So this is the lab and this is the whole team, and I thank you for listening to my talk and for giving this opportunity, for sharing our experience with you. Thank you.
Thank you, Kamran Hocam, and welcome.
If there are any questions, I'd love to answer them at this point.
I have one question before the students, if you don't mind. I'm a cell biologist, so I was wondering if you're, modeling your system more like into in vitro. Like, do you use any cardiac cells, or do you work with people who are in cardiac cell culture working projects?
That's in the future, and it's always going to be in the future, I guess, because all we can do is we can test the pump in a preload afterload type of circuit for hemolysis at this stage. They see if red blood cells are being destroyed, the white blood cells and platelets and all the others. That's really a surface problem. So it takes a little, this whole setup is too crude for the type of research that you're talking about, that requires fine work. This is too crude. We have gear pumps, we have pneumatic interfaces and all that are gonna create a lot of artifacts in the interface deposition of proteins, or cell destruction, or cell spreading, and all that. So what we can do is we can take the surface of the pump, which is being done actually, which is going to be titanium, maybe sintered titanium, maybe just smooth titanium, and then we can do cell interaction tests on that type of artificially inert, surface, I guess. Other than that, there's going to be too many artifacts.
What about 3D modeling? Can we use those pumps for 3D modeling, like organoids?
3D modeling of what?
Of aorta tube that you're trying to, with the pumping system. Maybe we can imitate the pumping system in the 3D organoid structure of heart.
Yes, of course. You can, for example, look into the sites of anastomosis of the outflow graft, for example. How would you angle the graft and the aorta, or at which point in the ascending or descending arch of the aorta? You can do the hemodynamics, prediction of the hemodynamics after, like, for example, implanting it into the abdominal aorta, for example. And that research is being done. It's a very useful research. But I tell you, in the surgical theater, the surgeons are really preoccupied with getting the patient out to the ICU alive. All right? They really, the angle of the anastomosis, the number of sutures, and everything, that's really secondary. What they want is, it's in their mind is just to leave the operative scene with the patient intact. So there is really a mismatch between academic research and clinical surgical application. We engineers, for example, can be sometimes removed from the realities of the clinical application, and we can overthink some of the aspects of it, which are not going to mean much to the clinician. But in a teamwork where the surgeon and the engineer and the students are working together on the development of the pump, of course, things are different. The surgeon will tell you the real problems that he or she faces in the operation, and then the engineer is going to relate to the doctor the capabilities, theoretical and practical capabilities that he or she can offer him. So there's going to be a really nice harmony and match between the two seemingly very different environments. If you can create this collaboration between the hospital and the university and the industry, that triple collaboration, that's really the optimal. Then what you're talking about, the 3D modeling, preoperative design of the surgery, patient-specific pump design, all this can become possible. You have to be in touch with the surgeon at all times in the R&D process. I'm talking about the engineer. And the surgeon also, sometimes they underestimate the intricacies of the patient management with the pump. For example, what we used to do in Houston at Texas Heart Institute is we would offer training to surgical teams from different parts of the world. They would just come in, do a couple of operations on a couple of animals, implant the pump, see the patients, and then go away, and then go to their home country, and then do the implantation. The implantation is really the easiest part of this. You just tie together two parts of the two anastomosis, two grafts, all right? The most important thing is what's happening afterwards, the management of the patient in the ICU. And that's the job of the cardiologist, of the immunologist, of the pathologist, of all teams, of the nephrologist, even the neurologist. So it takes a whole team to pull a patient from deep heart failure back into normal life. A whole team, and that includes the engineers, of course, but the surgeon and the cardiologist have to be trained for a while in the animal laboratory in order for these pumps to be successful. Otherwise, the surgeon is going to put in the pump, the patient is going to come out of the OR, but he or she's going to die in the ICU, and the whole money is going to go out, and the patient is going to go in the grave. But the surgeon goes on the newspaper. That's a very unfair situation, which needs to be remedied, especially for developing countries like us, or countries that refuse to be developing like us. So we really have to create that mindset, this ultra structure in our minds for collaborative work. Anyway, I think that wasn't the answer that you were looking for, but
I still have the hope for the future. There's a possibility to work with, together.
Yeah, working together with the surgeon is the key. You have to hear the real problems. You have to hear the real application possibilities. So that's the most important thing.
There is one question on YouTube. Probably you're not seeing it. I can read it. One student asked that, I was wondering, why is the whole heart being modeled numerically, like adding the venous system and so, when the main point is to work with the left ventricle and the aorta? That's the question.
All right, that's a good question. The left ventricle receives the blood from the venous circulation. So in order to reproduce the hemodynamics of the returning blood to the heart, you have to do the other parts of the circulation as well. But also, to complicate matters, there are a lot of feedback mechanisms in the body that are at play when the patients are failing, for example, or when you're exercising, or when you're sleeping. For example, if you exercise, your leg muscles are going to squeeze more blood back into the heart. So the venous return is going to increase, and the heart has to pump more to put it out. But when the heart pumps more, cardiac output increases through Ohm's rule, which means pressure equals flow times resistance. If the flow increases, your pressure is going to increase, which means your arterial pressure is going to go up. So if the flow increases twice, then your pressure is going to increase twice, which means that your pressure is going to be from 120 to 240, which is not compatible with life. So the body has to use a feedback mechanism to reduce the resistance, for example, of the arteries, so that your pressure stays pretty much the same. So those mechanisms need to be simulated in your virtual system in order for your model to reflect heart failure physiology properly. Otherwise, it's not going to be an accurate description of the problems that the pump can face in the body of the patient. So you really need to, you probably don't have to put in a reservoir for the kidney or for the intestines or for the big toe. All right, you don't need that, or for the brain, but you need to have extra mechanism like the coronary circulation is very important in managing the cardiac behavior. So you have to take into account all these extra details with extra reservoirs, extra capacitances, which increase, of course, the order of the system, the dynamics of the system. So if you were to do that in the benchtop environment, that it becomes impossible to control. So we lump all that into the numeric part of the hybrid circuit. There, the computer can deal with it in no time. Did that answer your question?
I think you answered it pretty well. There's one more question. One person is asking if this technology might have any side effects on living things.
Oh, that's a good question, and I'm glad that there are questions actually, because it means that people are interested in this, and that was a good question. Of course, it has many side effects. That's why these patients are not surviving forever. They are dying of complications, not only of heart failure, but of the pump as well. For example, if you there are very interesting paradoxes that we have discovered in the animal laboratory and in the clinical situation. For example, when you, if you want to try to help the patient, the first thing that you do instinctively is increase the pump flow, right? So you send more blood to the patient, which you think is good, but actually it's not good. Too much of anything is bad, even oxygen, even water, and too much blood increases the pressure in the ventricles, in the arteries, and then it causes damage to the walls of the arteries, and blood starts leaking, and you have internal bleeding in these patients. Then you have all sorts of activation mechanisms that are going on, like complement activation, immune system activation. You have embolic problems. You have, as I said, bleeding. Also, you have infection problems. Serious, very serious infection problems that you lose patients from. So the technology has a lot of side effects, but you have to think of it this way. These patients, the life expectancy of these patients is in the order of months when they come to us. So when you put the pump in, these patients are gaining at least 5 more years of life. And you have to look at it that way. And with the improvements in the technology, of course, we're gonna hopefully reduce these problems, and it's not possible to make a really problem-proof pump technology, but at least you can reduce the suffering of these patients to a great extent, to a very great extent. But yeah, the pumps have very many adverse side effects.
Well, thanks. Well, there's one more question. What is the most important factor that determines the stability of the pump?
What is the most important factor that determines the stability of the pump? Stability in terms of the amount of blood that needs to be sent to the body, I guess. I guess that's what you mean. How do you know how much blood, and how do you make sure that the pump in a stable manner sends that amount of blood? Of course, the most important thing in that sense is to adjust your reference value, right? And then to design your controller, right, to follow that reference, to track that reference. In order to be able to do that, you have to know the dynamics of the system. And in order to know the dynamics of the system, you have to know the parameters of the system in the dynamic equations, in the differential equations. So the parameter estimation is very important. If you want to control something, you need to know that something to the deepest detail. And in a mechanical, hydraulic, and rotational system, that knowledge arises from the knowledge of the parameters, like the inertia, like the friction, or the bending moments, those kind of things, the mechanical things. And also you have to minimize the measurement noise, and also, very importantly, you have to have knowledge about the hemodynamic parameters, like the pressure, for example. You adjust your pump according to the instant values of the pressure and the flow and the volume. Okay, so you need to know that. So you have to have sensors in the patient at all times, and those sensors have to be self-powering, wireless probably, and hemocompatible, and highly dependable. We don't have that technology yet. So most of the things that we do for control is based on guesstimates. So that's why system estimation techniques are very important. Kalman filtering, for example, designing a Kalman filter for the observer design, state estimation, all these, the control topics, those are signal processing and control, and also sensor technology. So there's a lot of unsolved problems. This is a very uncharted territory, and there's a lot of potential for research, a lot of potential for learning, for publication, for application, for training. It's a good area for students. Biomedical engineering, electrical engineering, bioengineers, control engineers, mechatronics. So that was a good question, though. Thank you for that question.
Well, thank you for answering. Well, I think there's no more question, and I'm going to end the session, the morning session. So we will have a break for 1 hour for lunch. After lunch, we would like to see you again with our new speakers. Thank you, Kamran Hocam, Özgür Hocam, Halil Hocam, for your speech. That was very good, very informative.
Thank you.
Thank you very much. So I will see you guys after lunch.
Congratulations for a very nice organization.
Thank you. Thank you.
You're welcome.
Welcome again, all of you. Our first guest after the break in Nur Mustafaoğlu. Nur Mustafaoğlu completed her undergraduate and graduate studies at Istanbul Technical University. She is currently in Sabancı University, and she will be with us with the subject of in vitro human blood-brain barrier models. And now I turn the floor over to Nur Mustafaoğlu.
Hello. I hope all of you are doing great today. It's Saturday and it's beautiful outside. So thank you so much for reminding me for this talk and staying with me in this beautiful weather today. So basically, let me start sharing my screen. I hope you will be able to see my entire screen. Can you see it?
Yes.
Thank you. So let me actually start sharing my experience to at least to help some of the students to find their path. And I will also describing my path as well. I graduated from molecular biology and genetics program from Istanbul Technical University. At the same time, I was doing my double major degree in physics engineering. And I also did my master degree in nanoscience and nanoengineering in the same university during my master degree. At that time, I was so interested in biophotonics, and I applied to Fulbright, received a scholarship, and moved to US to get my PhD in bioengineering. There, I actually studied on biosensors and their applications for enhanced detection of the different diseases. And there, actually, I had like some extra project, a minor project that was not in my PhD thesis at all, but I was so interested in delivering drugs to the brain, especially metastatic drugs, to cure the metastasis cancers in the brain. And then I realized that the models that I was using is not the right models. And I decided, okay, this was the minor project that I was focusing during my PhD, and it decided to focus it more and spend more time on that project and learn different models to test my designs, new drug delivery systems on advanced models. And I went to Harvard University, Wyss Institute for Biologically Inspired Engineering, to learn like new approaches for modeling the different functional organelle systems. So today, actually, I will be describing some of my journey from there to here at Sabancı University, how I ended up actually launching my own laboratory, focusing on the blood-brain barrier disease models, healthy and disease models. Let me actually start describing what is the blood-brain barrier. As you know, the brain is one of the mysterious organs in these days. Even we learned a lot of information about the brain, but we are still missing so many things, including its functions, its cells. Each day we are realizing, okay, there are so many different types of neurons in the brain, and they are functioning in different specific they have like quite very unique and specific functions for different purposes as well. And in the disease systems, we mostly focused on like glial cells, astrocytes, pericytes, neurons, but we rarely focused on the vasculature systems of the brain. So when I'm talking about the vasculature system of the brain, that I'm actually mentioning mostly referring to blood-brain barrier. As you can see from the right top image here, this is actually a human brain. I don't know if you can see my cursor though. Let me try to show. You can see it perfect. Thank you. So here this is just the vasculature capillaries of the brain. So it removed all the other cells, neurons, astrocytes, pericytes. Once they are removed, you ended up having just the capillaries that just the blood is flowing through inside the brain. The number of those capillaries is about 100 billion. And if you look at their network length, when you basically open them up, you will end up having like 650 kilometers length of the capillaries. This is basically like the way from Istanbul to Ankara. And the surface areas, if you open the capillaries into a flat surfaces, you will end up having covering a like small studio apartment, like 20-30 meters square. And basically, you can see some of these capillaries are large, some of them are much smaller. So the diameter of these capillaries is changing from 3 micrometer to more like 7 micrometer, like almost twice of it. So what you are seeing this is the blood vessels. Obviously, they are covered with the endothelial cells, the pinkish color here. You can actually, if you zoom into one of them, the pinkish color over there, it's the brain endothelial cells. Those are quite specific endothelial cells, which are like their protein profile, their expression levels of the proteins are quite different than the other endothelial cells in the other organs. And they are covered with the pericytes. The pericytes basically surrounding the endothelial cells like this, and we will be seeing the astrocytes and feeds on reaching to the endothelial cells to be able to connect the blood vessels with the neuronal cells, which are a little bit further inside of the brain. So, as I just said, these capillaries in the brain. They are a specific formation of the brain and endothelial cells, the capillaries, and they are quite different than the other endothelial cells in any other organs. And if you take a cross section from these capillaries, you will end up seeing like this. This is the lumen where the blood flows, and we are seeing an endothelial cells that basically surrounds the lumen. And there are some important proteins, we call them tight junction proteins and adherent junction proteins, that makes these endothelial cells specific, because the expression levels of these tight junction and adherent junction proteins in the brain endothelial cells much higher than the other endothelial cells in other organs like liver, kidney, lung. That makes these cells are tied to each other quite strongly. The spaces between these endothelial cells, like in Armstrong levels, and that eliminates many of the foreign molecules, like bloodborne pathogens, toxins to enter to the brain. So basically, the purpose of these specific capillaries in the brain is protecting the brain. And I can say this is a very specific structure of the endothelial cells, but also like with the pericytes, the basal lamina specialized in this around here. There are also other important factors, important proteins that equilibrate the structure and tightness of the blood-brain barrier in the brain region, and that can be expressed in other cells like pericytes and astrocytes around here. One thing I should emphasize is this structure in the blood-brain barrier, and throughout the brain. Basically, it's not homogeneous. So it is a very complex and dynamic structure. And if one part of the brain, if one type of tight junction protein is expressed a lot more than the other part of the brain, so we can say it is not the same in the entire brain. And it regulates the entry of different things, nutrients, blood-borne molecules into the brain, and it preserves the ionic homeostasis within the brain microenvironment. Those are all good things because we will like to protect our brain, right? So that's the reason that the blood-brain barrier, or some scientists call it blood-brain barrier interface, because it's quite complex and dynamic, is evolved in that way just to protect the brain. But on the other hand, that in the case of the diseases in the brain, that specific formation of the endothelial cells eliminates many of the drugs. Basically, any small molecules larger than a 400 Dalton cannot cross the blood-brain barrier. Basically, it limits the many of the drugs to entering the brain. Therefore, it becomes the major challenge for the treatment of the brain diseases or brain-related diseases. That is mostly because the high expression of the efflux proteins like BRCA or P-glycoprotein. So that's basically blood-brain barrier. We can say it's beautiful in one sense, but in case of any problem in the brain, it becomes the most challenging barrier for the clinicians for the treatment of the brain diseases, especially with the systemic delivery of the drugs to the brain becomes almost impossible. What else we know about the blood-brain barrier is in healthy conditions, it's functioning properly and well, but in the disease conditions, we actually don't know much about it. We know that in some certain disease conditions, like Alzheimer's diseases and brain cancer, it became leakier, or in epilepsy conditions as well. It's basically, this is an image just indicates that if you inject a dye into the brain, and if it becomes leakier in a certain part of the brain, the dye will diffuse to in some certain regions. But in those conditions as well, even if the brain is leakier, some of the expression of the PGP or BCRP, the efflux proteins, the entry of the drugs to the brain becomes remains still challenging. So when you say, okay, the gap between the endothelial cells is now open, but most of the drugs are substrate to those proteins. They cannot still enter to the brain and reach to the disease site. So it is still needs to be understand what is happening, what is the protein profile of the endothelial cells under those certain disease conditions as well. So we also still don't know what is happening actually to the blood-brain barrier in these functioning conditions too. So whether or not the blood-brain barrier disrupted before this disease is happening, so it may cause of the disease disruption of the barrier may be the reason of the disease, or it is disrupted after the disease happened in the brain. So this becomes chicken and egg problem, and it is hard to identify those things, especially for the human brain, because we are not always monitoring healthy brain conditions, and we don't know when the disease is started, when the the blood-brain barrier opening, early detection of the blood-brain barriers opening is occurred. So the research in these cases are still being explored, actually, and it in last few years, I should say, it became, the scientists realized, okay, we were focusing more on the internal peripheral cells in the brain for these type of diseases. Maybe the brain capillaries, brain endothelial cells, an important marker for those type of understanding those type of diseases as well. So the research is becoming really popular in these days and important, actually. And actually, as I just said, there is not much drugs, especially like for systemic entry of the drugs, actually approved for treatment of the central nervous system diseases, and the market is growing insanely. And this is the data, just I got it from grandviewresearch.com, and it says the market size for the treatment of central nervous system therapeutic market, basically it was about $77 billion in 2016, and now by the 2025 it is expected to be over $150 billion. So it says that the research in these cases for understanding and developing new therapeutics and understanding the diseases, drug delivery systems, is actually quite important for young scientists like you. So that's the era, actually, you can find a way to live and a way to understand the brain conditions too. So I was actually telling you what is happening, how we can just like the blood-brain barrier is quite tight, so that many drugs cannot enter the brain. But obviously, we are like having our brain nutrition, so it is still functioning. There are some ways, some important materials like glucose, amino acids, some important molecules can still enter to the brain, so that the cells in the brain, neurons, are getting fed and they're still functioning while we are actually living. So there are some pathways for the brain that is known, and this is one of the very famous schematic, especially for the blood-brain barrier world, and this is from Dr. Abbott, and I think this is one of the earliest form of it, so you can see different versions of this schematic as well. And in this schematic, it has highlighted some pathways, the paracellular aqueous pathways. If the molecules are water soluble, they can enter between the cells. If they are lipid soluble, so they can basically transcellular use the transcellular lipophilic pathway. Some of them, like glucose, amino acids, some amino acids and nucleosides, can use some of the specific transporter proteins. And some of them, if they are really highly positively charged, like albumin and some other plasma proteins, they can be entered, encapsulated by the cellular membrane, because the cellular membrane is negatively charged, and they can cross to the brain side, from blood side to the brain side. But the ones that I described, they those are the pathways every single cell actually uses as well. So it's not specific to brain endothelial cells. Our other cells, our other endothelial cells are also using these pathways. There is one pathway, it's called receptor mediated transcytosis. In these ones, if a brain endothelial cells is expressing some receptor proteins higher than the other endothelial cells, like insulin receptor proteins or transferrin receptor proteins, then we can actually use these receptor proteins to target not only for delivering not only insulin and transferrin, but also mimic their functions and deliver some of the carrying agents as well. So, or we can conjugate some of the drugs or carrying agents to these proteins and deliver them together to the brain. Basically, use them as a shuttle system. Okay, so that's what I was trying to do during my PhD. I was basically creating some liposomal nanoparticles, something like that. They have the lipid formation and PAC cloud on top of it. What I was doing with these liposomal nanoparticles, I was adding a peptide sequence here that are targeting different receptor molecules that we know that are expressing on the brain endothelial cells. And I was creating these kind of structures, a peptide, a linker, and some additional moieties like lysine, tryptophan, and lysine for increasing the solubility of these peptides, so I can have these peptides to be expressed on the liposomes, and also be able to basically check the concentration of these peptides, and also a lipidic version, so I can incorporate these peptides into my liposomal nanoparticles. So I was designing different linker lengths here, and then just basically creating different formulations of these liposomal nanoparticles. And I can add different peptides that are targeting the different protein receptor proteins on the brain endothelial cells. So what I did in my initial test, I was using basically some cells, brain endothelial cells, and test them on the flow cytometer experiments, check these the peptides that I created, incorporated into my liposomal nanoparticles, whether or not they bind to my cells. And I identified some of the peptides, liposomal nanoparticles, actually binding to my cells quite properly, and they are actually also uptaken into the cells quite properly as well, but some of them fail to do that. So I choose the ones that are binded to my cells are also uptaken. And I tested different sizes of the nanoparticles, 50 nanometer, 80 nanometer, 100 nanometer. I tested different peptides that are targeting to transferrin receptors. And I used different linker moieties, some short ones, e.g. 6, and some long ones, e.g. 24. And I identified some of these formulations are actually working better than the other one. And I even went more optimization, load different densities of the peptides on the nanoparticles. I found that 2% of the peptide works the best. But it was the time that I realized, okay, what I should do actually have these nanoparticles to test them on in vitro systems, whether or not these nanoparticles cross the blood-brain barrier, right? So right now, from these experiments, they are actually binding to the cells and they are uptaken inside of the cells, but I still don't know whether or not they are crossing the blood-brain barrier. At the time, they're using the transwells, these basically some small inserts that have the membrane, a porous membrane at the bottom, and you can put this into a Petri dish. That can be 24-well Petri dish or 48-well Petri dish, depending on the size of the insert. So basically, you can grow your endothelial cells on top of these membranes. So if you have your nanoparticles, you can add your nanoparticles from to the top of the cells that you grow on this membrane. And if they cross to the bottom compartment, you can detect them and say, okay, these are past the blood-brain barrier, okay? But the one thing that I needed to make sure these cells that I'm seeing on the membrane, on the porous membrane, that I'm getting a very monolayer tight barrier formation. So I will be making sure that my nanoparticles are actually binding to the receptors on the endothelial cells, uptaken and crossing the blood-brain barrier. They are not just crossing in between the cells by diffusion, okay? But there is a way to determine the barrier integrity, which is called endothelial electrical resistance measurements. Basically, how you are going to do is we have an electrodes that we put inside of the insert and outside of the insert and check the resistance in between. So at the time I was using primary brain endothelial cells, and the resistance of the cells were getting like 6 ohm. These are like basically saying they are not resistant to anything, and they actually do not form a monolayer. So whichever that I was adding into the top of these inserts, they will be crossing the membrane, basically not the blood-brain barrier, because I cannot create a blood-brain barrier. And each time I was getting a different results with my formulations. I actually didn't know whether or not my formulation worked, or it was the system that is not working at all. So I realized I should use a different system for checking my formulations. So using the 2D cultures that I was already doing, as I was getting high throughput and low cost experiments, so I can test different formulations and different peptides, peptide-coded nanoparticles in quite short time. But I was using only one cell layer, and that one cell layer have a very poor relation to the in vivo conditions. And when I try to do more complex structures, like putting these cells onto membrane, try to understand the transcytosis assays, it did not work well, because this one cell layer does not correlate it with basically does not form the in vivo like blood-brain barrier integrity as well. And if I use the animal models, they can form high complexity, optimal cell-to-cell contact, but basically they are also with high variability. And the worst thing is mouses cannot correlate with the human data. And I was trying to target the human receptors, human proteins on the mouse models. And then the organoids. At the time when I was searching, they were just emerging, these models. They are self-organizing, and they create an optimal cell-to-cell contact, and they can be used for different purposes, like they can be transplanted into different organisms as well. but they also have some drawbacks, like hard to replicate, hard to visualize. And in my purposes, I was trying to create a very intact blood-brain barrier formation. It is hard to quantify that barrier formation because these organoids are lacking the vascularization. So I am interested in a blood container and the brain container, so I can check the basically transport from blood to the brain. And then I search for the microfluidic systems. With that ones that I can create an optimal barrier formation. It can create a high contact and easy effluent sampling, so I can flow my samples into the blood stream, and I can check they are transported into the brain stream, and they are amenable to drug discovery. And if I need to, I can use the interactions between the other organs too. Obviously, they also have some drawbacks too, like physiological systems, low throughput, and they are expensive. They are still expensive after all that research, but they are getting there because people are started using those systems quite often too. And currently, at the time, actually, it was not predictive yet to the human models as well, non-human primates and humans, but currently there are some clinical studies on the drugs that are identified based on the organ-on-a-chip systems too. So, but based on these, I identified the microfluidic systems may work the best for my purposes to identify and to screen my drugs. And I needed to learn what are those and how I could use them. So I went to Harvard University Research Institute to a group that are specialized on the organ-on-chip models. And at that group, actually, there were so many different organ models. I should say they are not creating the entire organ, but just the functional unit of the organ. So that is basic enough, but include the complexity of the functional unit of the organ, so it can be used accelerated drug development, and it can replace the animal testing with the human cell-based systems like this. And they were having more than 20 different functional units, including the 2 different forms of the gut, small intestine and colon, and like 2 different functional units of the lung, alveolus and small airway, 2 different functional units of the kidney, proximal tubule and glomerulus, bone marrow, and I was involved in creating the blood-brain barrier model too. So here is just to make you a little to understand it in a little bit visual way, a short video. You can also find this video at Research Institute's webpage too. It just describes these models too. And on first got a lung on a chip system. Basically, you can see in the lung there is a breathing motion, and in this model there are basically a porous membrane. On the top of the porous membrane there is lung cells. At the bottom it's the capillary cells, basically endothelial cells. You applying the vacuum channels, you can actually create these breathing motions on these cells too, and that actually changes all the functions of these cells. And you can actually see they are simulating the white blood cells are going and engulfing a bacteria on top of the epithelial cells in this model. And you can see the live image and schematic image there too. And in the second model, it's schematized here. This is the gut model. There is a lumen, these capillary villi structures, and the when you apply the cyclic motions in peristaltic motions in our gut as well, you can see the 3D growing of the cells too. So basically, these organ chip models, you can connect also different types of model like organs through their vasculature channels and understand the metabolisms and understand the interactions of the drugs with different organs as well, if you're interested. What I was doing in my studies during my postdoctoral degree is actually using very similar microfluidic device, which has two channels separated by a porous membrane, and at the bottom of the channel, but at the bottom channel, I was incorporating induced pluripotent stem cell differentiated brain endothelial cells rather than the primary endothelial cells, because during my PhD, I knew that if I'm using the primary endothelial cells, I cannot create an high integrity of the blood-brain barrier. So I used stem cell differentiated brain endothelial cells, and I also used co-culture them with the human primary astrocytes and pericytes on top of the membrane. So the bottom channel was my blood channel, and the top channel was my brain channel, and it was separated by a porous membrane. So if I have a drug or anything that I wanted to test whether or not that it's crossing the blood-brain barrier, I can basically perfuse that molecule from the blood channel and check its crossing in the brain channel. And I can use this tested in the human cellular environment while everything is under flow, as in our capillaries too. One special thing that we did in that study is to differentiate these cells under some hypoxic conditions. Basically, hypoxic conditions, we used the developmentally inspired induction. So in normal conditions, we normally culture our cells into many % oxygen at the atmospheric conditions, but in the developmental stages, that is not the case. So we went to used like lower oxygen levels and to differentiate our cells in these conditions. And then after they are differentiated to endothelial cells, we put them back into the chips and culture them under normal conditions, as we will normally do in all of our cell culture systems too. After using these systems, basically, we ended up differentiating the cells quite well. We checked the endothelial cell markers like tight junction proteins, ZO1 and Claudin-5. Claudin-5, one of the brain-specific tight junction proteins. And we checked for endothelial cell markers like PKM1, we checked for transporter cell markers GLUT1 and efflux cell markers PGP, glycoprotein, as I was describing to you when I was describing the blood-brain barrier. And we saw this, the expression of these markers were entire the chip systems, and we actually identified other injection and charge junction formulations with the electron microscopic images as well. So far, using this hypoxia-induced differentiation protocol, we were able to get the brain endothelial and endothelial specific cell markers. Then the question is, okay, can we also get the high barrier formation too? And for this, we use the specific chip system that has some of the electrodes inside, so we can measure the impedance values of these endothelial cells. So in this system, we see that the primary cells that I just described to you, the ones that I used during my PhD. So as expected, they do not form any barrier. So the impedance values were quite low, and it was quite correlated with my PhD studies. So, and I used a transwall model in the system actually I used during my PhD, but in this case I used the stem cell differentiated cells in these transwell models, and the barrier integrity was quite high. It started high, but since I cannot flow of the media, I cannot simulate the blood flow conditions in these systems. Over time, the barrier integrity dropped. So in 15 days, it dropped quite well. And when we seeded these cells, iPS-derived brain endothelial cells, into these microfluidic systems and keep flowing the media under physiological conditions, we could be able to culture these cells more than 15 days without changing any integrity of it. So far, we saw that the protein markers, we saw that we can achieve like quite high in vivo-like barrier integrity if we use the brain endothelial cells, iPS-derived brain endothelial cells, and if we can culture them under flow conditions. So both cases are quite important. And then the question was like, okay, are they going to function as they were doing in the in vivo conditions? One answer for this, we checked different molecules that we know that they are substrate to the P-glycoprotein. So that means in normal condition, these molecules, we tested 3 of them, rhodamine, DOC2, and stolopram. So in normal conditions, when we injected them to the blood channel, they could not cross the blood-brain barrier. But when we inhibit the protein, PGP protein, so they should be able to cross the blood-brain barrier. So what we saw this effect when we use the blood-brain barrier chip model under flow conditions, and actually, when we use the same cells under static conditions like Transwell model, the trend was there, but the effect was statistically non-significant. So that tells us, okay, the cell source is quite important. We need to start with a really well-characterized cells, but the flow conditions to maintain the function of the blood-brain barrier is a lot more important. Okay, so far we know that we have the barrier markers, we know that we have the high barrier integrity, we know that the function, we can have a functional blood-brain barrier formation on these chip models. Then the question is, can we use this chip model for testing the drugs crossing the blood-brain barrier? And one thing that we wanted to test is some of these mechanisms. The first one, we collaborated with medical doctors from Boston Children's Hospital, and they told us what they are clinically doing like in the brain cancer patients. Basically, they are injecting mannitol, and which is an hypertonic solution to shrink the cells, so to create a leakier barrier at the same time delivering some of the large molecules and chemotherapeutic drugs to the brain for the treatment of the brain cancer after the surgery, basically just to remove any of the remaining tumor tissues. And we wanted to test this on our chip too. So can we actually, when we use these hypertonic solutions to open the blood-brain barrier, which we did, we applied this mannitol to the system and simultaneously watch the barrier integrity. So once we applied to the hypertonic solution, barrier integrity dropped, and we applied it 1 more hour while delivering the drugs, and then we stopped and switched to normal isotonic solutions. And we observed that the blood-brain barrier recovers back because the effect of the mannitol is reversible. At the same time, we saw that this large molecule can cross the blood-brain barrier during the opening phase. And once we switch back to the isotonic solutions while the blood-brain barrier is recovering back, the basically transport of these large molecule can get lower and lower. And it was the same for these large drug, which is actually an antibody that can cross the blood-brain barrier, and then while the barrier integrity recovers back, it just gets lower and lower. So this was one of the first experiments that we intentionally opened the blood-brain barrier using the hypertonic solutions and recovered back as it was actually happening in the clinic. The other thing, but this was a physical opening of the blood-brain barrier. So what we wanted to test is actually, can we open, basically, can we deliver the drugs without actually opening the blood-brain barrier at all? So we tested a peptide that is called NGF-PEP2 that is basically targeting the LRP1 receptor protein on the brain endothelial cells. And we basically, just for the proof of concept, we covered quantum dots with these peptide and the scrambled version of these peptide. And the peptide itself could cross the blood-brain barrier 3 times more efficient than the scrambled version of the peptide. And that was also showing that, okay, we can actually deliver specifically some of the carrying agents targeting some of the receptors basically to the brain. Using these systems, we can actually differentiate. We actually tested this with a little bit more challenging system as well. We used antibodies, anti-transferrin receptor antibodies, 2 of them actually, two clone of them. One of them is 13E4, the other one is MEM75. We know that 13E4 binds to transferrin receptor without any dependence on the pH, whereas MEM75 binds to receptor with a very high binding, but at the drops of the pH, its binding affinity gets lower, and then it can release from the receptor quite easily. And basically, when it's bind and get uptaken in this intracellular vesicles, basically the binding affinity of its drops, so it can